Sorry, I realized I was muted, so my apologies for that. So this is the second live streaming for the ZP Developer Zone members. And so we'll start the presentation sort of now. So let me just do that. Okay, cool. So the first thing is thank you for joining us today. I'm delighted with some of the feedback we had from last week. So what I'll do now is just go through some slides. I just want to say really good job to the guys in ZP in Indonesia. They've actually registered us at the moment. We're now registered to be participating government tenders. So I think this might be very interesting for our colleagues in Indonesia, because some of the technology and some of the equipment that we have actually it can be bought now through government grants. So good job to the guys there. Today's talk, I'm actually going to focus on one of our members, Sirif. So what we like to do in the ZP Developer Zone is we like to I like to take a look at our members and take a look at their work, and try and make the presentations specific to those people. So when you become a member, then obviously ZP has taken a special interest in you. We want all our members to basically in the end be successful in terms of successful in making papers, or even successful in actually making products. So the whole sort of business of Zimmer and Peacock is to try and get as many people to the market with biosensors as we possibly can. And I can see, I'm just watching the live stream now, and I can see that Hasim is just saying, Sirif, if you have any questions, feel free to ask. There's also the Discord server as well. So, I mean, we do post on that, so you can get hold of us there as well. All right. So what we did is we had a look through some of your papers. And the nice thing about science is it's quite universal. So, I could read, that you were interested in kind of DNA and you were interested in bacteria. And I think when I sort of dug down into your papers a little bit, in order to identify bacteria, you were using a piece of code which is called 16S rRNA, and this is a known, it's known in the literature that if you want to identify bacteria, and you want to have a more definitive identification of the bacteria, then so identifying this code and sequencing this piece of code will actually allow you to identify the bacteria with greater certainty. Now, when I read papers like Sirif's, you actually, the workflow that's often talked about also, is actually that there'll be some bacteria, and within the bacteria, there'll be a piece of genetic code, and that piece of code will help identify the bacteria. So in bacteria, it's actually 16S rRNA, which is it's a piece of RNA that's part of the genetic code of this bacteria. Now the workflow is this: we have bacteria, and in it there's genetic material. So here I've labeled it up, that we have bacteria. There's some genetic material that identifies that bacteria, and now we need to actually identify the bacteria. So what we have to do is we have to get our bacterial sample, we have to extract that DNA, and then we have a whole series of sort of biochemicals. We have primers. Primers are the things that help you amplify, for example, DNA. We often have bases. So these are the sort of things that click together in order to form genetic codes. You have Taq polymerase. This is the guy that kind of puts all the bases together. And what people are doing is they take their DNA, they take that biochemistry and then they take it through a sequence of temperature cycling. So you hear people talk about temperature cycling and polymerase chain reaction, and what they're doing is they're denaturing it at one temperature, they then take it to another temperature where it anneals and then it extends. So sort of denaturing is taking the DNA apart, you bring the DNA back together, you anneal it and you extend it. So basically what happens is that we have what happens is you take a bacteria, you have to get your DNA out of it. You put it into basically a biochemical reaction. You temperature cycle it, and your one piece of genetic material after cycles becomes many more pieces of genetic material. So you're basically amplifying one piece into many pieces. And this is known as PCR. I know this is really known to people, but I am going to get to my point in a second. So when we read papers like those of Sarif, he's interested in a piece of genetic code because that piece of genetic code will help him identify the bacteria. But his workflow is he has to get his bacteria, he has to get his genetic codes, he has to amplify it, and then he has to identify it. And people often use a technique called gel electrophoresis. So gel electrophoresis, they separate all the genetics on a gel by applying a really large voltage. So a very large voltage is applied. The DNA travels in the field generated by the voltage, and it separates out. Now, I've just spoken for 6 minutes on this, and that in some ways reflects, actually, it's quite a piece of work to do this. So ideally, what people would love to do is have some bacteria and detect it on a biosensor. So rather than going into the lab and extracting their DNA, amplifying their DNA, and then identifying their DNA and even quantifying their DNA by gel electrophoresis, they'd just like to put it onto a biosensor. I'll just grab an example of a biosensor now. So I just grabbed one off my shelf. So I just want to, I know many of you are familiar with this, but the whole beauty is can we reduce that workflow down to something that's much smaller. And so in this talk, I'll try to demonstrate that I don't think we can, I know we can. So let's do that. Right. So what's happening here now is, now this is the second webinar we've done for the members only. In the first webinar, we actually said, in that webinar, we said, if we want to identify some compounds, we can use a technique called MIPS, molecular imprinted polymers. So if you're not familiar with that, there's another webinar in this series. I take a look at that. But the only reason I bring that up now is because it's basically the same thing. We're going to take a biosensor and we're going to take the working electrode and we're going to functionalize it. Not as we did last week, where we talked about using molecular imprinted polymers to functionalize it. We're going to functionalize it with what's called a capture probe. So if Sarif is interested in a piece of the genetic code called 16S rRNA, then we're going to have to find a capture probe, put it on the working electrode, and then that will take what's effectively an electrode and turn it into a sensor, because now we functionalize it to make it specific. So similar principles to what we talked about last week, but now we're going to talk about a different type of functionalization. So here, I've tried to summarize how one does this. So we take this is a screen printed electrode. This one is gold. I've deliberately used gold because people often use, in this kind of work, self-assembled monolayers, SAM, self-assembled monolayers. I will, on the ZP website, we do show you how to kind of make a self-assembled monolayer. So To make your sensor, you take a gold electrode and you immobilize what's called a capture probe on the surface. And you do it using a technology called self-assembled monolayers, which is SAM layer on gold. So you have your bacteria, you extract out your piece of genetic code that you're interested in, and then you bring that sample to now your biosensor, and they hybridize. So this single strand of genetic code here has now hybridized with this code. And what it's doing is it's doing this on the surface of the electrode. So it's actually changing the surface properties. And electrochemistry is really good at identifying changes on its surface. And this modification of the surface is specific because DNA or genetic code is really good at binding to genetic code that is compatible with it. But in fact, if you don't have the right if you don't have the right base pairs, it doesn't bind so well, or it doesn't bind at all. So this piece of capture probe gives you specificity towards this piece of genetic code. And so that binding can be quite specific. Because I want to identify that the surface has changed, I have a reporting molecule in my buffer called ferrocyanide. And I know we've talked about ferrocyanide in the past, so I'm just going to bring back an old slide that I've used in the past. This is the cyclovoltammetry of ferrocyanide. On a clean electrode, maybe where there's been no binding of the DNA, you'll get a signal that looks like this. The peak height is proportional to the ferrocyanide in solution. But as the DNA or the genetic code binds to the surface, this peak height will decrease because we're effectively blocking the surface. Now, I do have a video on how easy it is to do an experiment like this. I'm just going to play that video for you quickly. So I'm just going to bring this onto my screen. So the kind of equipment that you need, this one is a early version of our Anapot. This is a little screen printed electrode. And effectively, all we're going to do in this experiment is, I'm just going to, in the first instance, I was just taking buffer. So this is buffer without any ferrocyanide in it. We put it onto the electrode like that. And then we'll press play on the software. I'm going to go quite quickly now. So the experiment will start in a minute. Now this one is very boring because this is buffer without ferrocyanide. So I'm effectively doing what's called a baseline measurement. So I'll fast forward it through a bit. So now I've probably got my baseline experiment done in this video. Now what we're going to do is we're going to clean off just the buffer, and we'll pipette on ferrocyanide. So there's a new drop on the sensor. I'll go back to the software. I'll click a green arrow, which is the go button. And the experiment will start. So you see this big peak? There you go. That is how to do the cyclovoltammogram of ferrocyanide. It's really quite straightforward. And this is kind of why I do like electrochemical techniques, because they can be really straightforward. It's not hard to necessarily set up these experiments. So I brought that up. So I'll go back to the main presentation now. So I brought that up because it is easy to use ferrocyanide in experiments, and it's relevant to this conversation because I would like people to take electrodes, immobilize what's called a capture probe on the electrode, then they can bind their genetic code of interest, And then they can see that binding by the blocking of ferrocyanide. And the nice thing about electrochemistry is there is such a mass of online literature about this that, what I'm actually describing has been done, but it's not been done for the kind of molecules or bacteria that you guys are interested in. But there's some good precedents for it. In this paper, somebody's taken a gold electrode. They formed the self-assembled monolayer. They can then interrogate their monolayer. See, with FeCN6, they're basically talking about ferrocyanide. They record an electrochemical signal, and then their target molecule comes in, binds with the capture probe, blocks the ferrocyanide, and the signal goes down. And it goes down because they're effectively blocking the surface. Now, what's nice about papers like this is they actually use what's called a gold disc electrode. So it's good science, but it's not the kind of science that could translate into being a low-cost medical diagnostic or a low-cost test for food bacteria. It's not able to do that. Now, this is, again, from the paper. So, afterwards, I'll put this video up online so you'll be able to go through this again. But they do show here quite nicely that as they increase the concentration of their bacteria, the peak height of the oxidation of ferrocyanide into ferricyanide goes down. So it really validates, I think that if people are interested in doing things like bacterial detection, and they think that they would like to use the piece of code which is called 16S rRNA, then you can make a capture probe for that piece of bacteria. You can put it on a gold electrode. You can use the electrochemistry of ferrocyanide, and that will then give you a signal proportional to, first of all, it will identify that the bacteria is there, and then the decrease in signal or peak height will be proportional to how much bacteria is there. So I've just talked about cyclovoltammetry, but actually when you read the paper, they actually use a technique called, I think it was square wave voltammetry. So in cyclovoltammetry, this is one of our, this is a repeat of a slide that we've done in the past, but I just want to show you that some of the basics that we talked about, where we talked about cyclovoltammetry, they're now coming back to play in actual examples of biosensing. But I said that in the paper, they use a technique called square wave voltammetry. So I'm just going to show you some software quickly, because I want to show you that, in fact, this piece of software goes with one of our potentiostats. I'll just grab an example of one here. So this is one of our potentiostats. We have several models, and this is what's driven by the software. So I'll just slide the sensor in like that. The reason I'm bringing up the software is because I'm saying to you that we've talked about cyclovoltammetry in the past, but now I'm saying actually there's all these other voltammetric techniques, including differential pulse voltammetry, square wave voltammetry, normal pulse voltammetry. The beautiful thing about electrochemistry as a technique is it's very easy to change the technique. It's just a drop-down menu, and you can change the technique. So I'm going to come away from the software now, but I'm going to say in this paper they use a technique called square wave voltammetry. It's very easy in software to go between cyclovoltammetry and square wave voltammetry. And now I'm just going to give a little illustration of yeah, we have talked about cyclovoltammetry, but we've not talked about some of these other voltammetric techniques. And there's normal pulse voltammetry, where rather than just sweeping voltage as a function of time, we're doing these little pulses. Differential pulse voltammetry, where we're doing pulses and we're stepping up all the time. Staircase voltammetry is quite straightforward. You're just doing step, step, step. And then they were using a technique called square wave voltammetry, where they have a voltage, they step down, they step to a new voltage, they step down, they have a new voltage, they step down. A square wave voltammetry has a good reputation for being very good for techniques where the molecule of interest is in quite low concentrations. So in this bacterial example, they were probably concerned that the 16S rRNA was in quite low concentration, so they decided to use square wave voltammetry rather than cyclovoltammetry, and I think they're probably right. And it's not to worry too much. No, I don't know these techniques. It's literally like computer games. You can just choose the technique, and if you're not sure about those parameters, either use the parameters from the paper or just contact us on the Discord web chat room. So we have a really good chat room. I'm probably on it at the moment. And if people in our ZP developer zone have questions, you can contact us there, and we'll try and answer them through the chat, or we'll get you into an online meeting and we can advise you that way. If you're not sure how to form a SAM layer, or you don't know where to start, then I have a link here. If you ever Google Zimmer and Peacock forming SAM layer on gold electrodes, then that will give you a good starting point for how to do a SAM layer, a self-assembled monolayer. I just wanted to, it's always nice. Now, I'm interested in the research, but of course I'm really interested in the, in the commercial exploitation of electrochemistry and biosensors. So I just wanted to kind of make you aware that it's one thing for me to say this kind of techniques are used in academia, but in fact, I've also found a reference, a commercial reference, a company that's based out in California, USA, where they are actually doing the electrochemical detection of 16S rRNA. Their method is more complicated than the one I've described today. So my advice, I bring this up because it's interesting to know that, it's not just academic research. You can, in fact, take this kind of technology and go to the market with it. And I also want to say that I can just see that Sarif has just said he's present. I hope you can watch the video, Sarif, afterwards and sort of capture everything. Or see everything, rather. But anyway, it's nice to know that this is done commercially. My recommendation is, the way they do it is actually quite complicated. So I actually think that the method that was described in this paper and I've described today using ferrocyanide is much simpler. So I always want these webinars. I just see Hasim has just said, Sarif, you're here finally. So yeah, Sarif, but the video will go online afterwards, so please watch it again. So I just want to do a kind of summary. So our ambition within the ZP developer zone is to help our members design sensors that can make a real impact. So, if you're doing something in an academic setting and actually, you think, I really would like to commercialize this, and you are a ZP member, then you're in a good place, because at least being in partnership with ZP, there's a chance that we can actually commercialize this and put it on the market. I would absolutely state that electrochemistry and electroanalytical science in general is really good for monitoring chemistry and biology. I mean, last week we talked about polyphenols and oxidative properties. This week we've talked about genetic detection, and the science is still good. And what's really interesting for me is the science remains consistent. We talk about cyclovoltammetry, we even talk about ferrocyanide a lot, and yet the molecules stay consistent and the science stays consistent, but then we're just talking about new applications from it. And the identification of bacteria using this kind of genetic identification, there is academic literature for it, and there's also commercial literature for it. So I'm just watching the chat online, and I can see that Hasim is saying, if you've got any questions, let's get into the Discord server. So I agree with that. I'm just going to bring up the Discord server. So if you're a ZP member, please join our, please come into the Discord server. We can have a chat in there. Otherwise, yeah, I've been chatting for 25 minutes. These talks are only meant to be 30. So in summary, this week we've focused on Sarif. I took some of his papers. We identified he's interested in bacteria, and he's interested in using the genetic code for actually identifying that bacteria. And we've shown that you can actually take that wish and reduce it down onto a biosensor. And if you do that, then you're in a position to be making a low-cost sensor for medical diagnostics, or maybe a low-cost sensor for I can see here that somebody's asking, do we have to make the single-stranded DNA in the sensor ourselves, or can we get it directly from ZP? It's a good question, actually, because at the moment, the ssDNA, which is a question that's just come up, at the moment, you would have to make it yourselves. I am quite interested in actually offering that as a sort of service from Zimmer and Peacock. We haven't done it yet, but I will start exploring that. So at the moment, if the barrier to you is making some of these genetic capture probes, like the ssDNA, single-stranded DNA, I think at ZP we are actually quite interested in doing that or helping you with that. So the quick answer is, at the moment, you would have to make them yourselves. But if that's a problem, then I think ZP can probably help you out on that. So I'll just check if there's any more questions. I don't think I see any. As I say, if you've got any more questions, come into the chat room later on, because what will happen is I will put this video will be up on YouTube, so you can rewatch the video. And in the chat room as well, I'll be putting a link to this presentation so you guys can have all the slides and etc. All right, so I think I don't see any more questions. It was a good question about the ssDNA, which came up, single-stranded DNA. I am interested in being part of that supply. So either make it yourselves or maybe talk to Hasim and the guys. All right, I think that's it for this week. We do have a bigger webinar coming up pretty soon, which is we're going to do a big webinar on electrochemical impedance spectroscopy. That's on the 6th of August. So we'll carry on doing, most Thursday there'll be private streaming for the members only, and then once a month we do a big streaming, and it will be for we'll do a big streaming, and this next one will be on impedance spectroscopy. Okay, cool. I appreciate it. And any questions, put them in Discord or contact Hasim and the guys, and speak to you soon. All right, thanks very much.